right, so stretch is about the x and y axis. So set your calculator to degree mode and use that window setting. So get out your calculator. I got my good version back. Okay. So, window setting. 60. Okay, go to mode key, convert to degree. Remember, your main setting is radian on a graphic calculator. So on the same graphic calculator screen, sketch the graphs of y equals sine x. So sine of x, equals bracket, and sine of 2x. Remember, math is not a sin, it's sine. Okay? So, in degree mode, that's why we're going from negative 360 to positive 360. Those are going to be degrees, your x values. There's your original. So we talked about this back in Math 20, just as we've seen sinusoidal curves. Okay, but we want to look at what happens when you change that argument, right? X, or in this case, maybe then 2x. What happens? So here, trace is on the blue. Okay, you can see it's got 2 cycles. If I cursor down, it goes to the y2. Now I've got 4 cycles. Okay, it's taking that original one and squished it. Okay, it's horizontally. So we call that a horizontal stretch. Okay, but it's not. Doesn't look like it's stretched out this way, right? It's squished in. So we always use the word stretch, no matter if it's like this or like this, like in the accordion, it goes back and forth, right? We always use the word stretch. If it's going to have more cycles like that, it's going to be stretched by a fraction less than 1. In this case, 1/2. Okay? If you, so here, because we replaced x with 2x, we say it's horizontally stretched. Horizontally is always about the y-axis, because that origin stays the same. But it's by a factor of 1/2. So that b value, you take the reciprocal of it. Okay. What's kind of interesting or nice to know here, this too, if you actually look at the graph, so from 0 to 360 is just from the right there. In your base graph, you have 1 cycle. Remember we talked about the period of a sinusoidal curve? It is 360 degrees, or 2 pi. So here, this is 1 cycle. Now we get 2 cycles in that same amount. And that's kind of a hint here, that 2. But when we talk about what stretch it is, it's stretched by a factor of 1/2. Okay? That means it's getting smaller. The period, the length of that cycle is smaller. It's half as much as it was before. Okay? So, remember that sine of 90 is 1. So the point 91 lies on the original graph. Its image point on the new graph then is what? So if we're stretching by 1/2, let's take a look here. You can graph it. So if you're on your original and you punch in 90, That's that first maximum. Okay? Where is it now? After the transformation? It's there. It's half of what it was, 45. So if I go and cursor down to my Y2 and put in 45, there it is. Okay? So the new point is 45, 1. Okay? You take what you originally had for x and you multiply it by half. You stretch by a factor. Factor means multiply by half. Verify your answer by using your calculator, which is what I just did. So now here, this is going to be x over 2. Y. Okay. Or you can get 1/2 x. Remember, those are the same. Okay, so when you're replacing x with something multiplied by x, it's a stretch. If that factor out front, that coefficient is bigger than 1, it's going to be compressed. Okay, so the result is compression horizontally. But we always use that same word. Horizontally stretched about the y-axis by a factor of whatever it is. It eliminates that because if you say, oh, it's been compressed by half, well then that's kind of like a double, double negative. You compress it by half, but then it's going backwards, so it's confusing. So if you always say horizontally stretched with the correct factor, it'll work its way up. Okay, so now we're going to do sine of 1/2 x. Obviously, going to be the opposite of what just happened. So here, you can delete that, insert. You can do, if you have the ability, you can do a fraction form. 1/2. Okay, you can go x over 2. Whatever you, either one, they're the same. You can go 0.5. There's your original. There's your new one. So now this has been stretched out. Okay. Now it's been stretched out. It's been stretched by a factor of 2. Well, there isn't a 2 there, it's a half. So it's the reciprocal of that b value. Okay. So this is always called, whatever coefficient here is always called b. The coefficient of x is always called b. So the original, if we're starting with this point and we're stretching by factor of 2, remember mapping notation, it is what it is. So we're going to take that original point, and our new one's going to be 180, comma 1. Right? So we're multiplying. This is going to be 2x comma y. All right, you can check on your calculator. Trace 90, there's your original. Now it's over here. So if I cursor down and go to twice, which is 180, I get that same maximum. Okay. So predict how the graph of the y equals sine x changes when x is replaced with 3x. So that's very similar to the first one we did. This number is bigger than 1. So that's going to be horizontally, horizontal stretch by about the y-axis, or down in there. You can put it at the end, but Okay, so if it's a 3x, that's going to be 1/3, the reciprocal. And you might think, why do we have to say about the y-axis? Well, we could stretch about different vertical lines. Okay, in this course, we're only stretching about the y-axis, but that's why you should put that in there, because you could stretch about different axes. Okay, or not axes, but you would have to physically. You would just, so if here's a line, you have a graph like this, you take the distance from that line and double it to have it. In terms of actually calculating it, it would be more complicated in terms of the...
You have to there's no equation.
Yeah, it probably is an equation, but... Okay, so then replacing x with 1/3 x. Okay, if you want to check, you might want to change your window, and so we can give you a suggestion there. Okay, so this is a horizontal stretch about the y-axis by a factor of 3. So remember, horizontal transformations, when you're translating, it's the opposite of what you would think. If it's x with x minus 3, you're going right. Okay? Opposite of what you would think when you think subtracting. That's because you're compensating for what subtracting 3 does. Here, if you have 1/3 x, you do the opposite of 1/3. It's multiplied by 3. Right? When you think about that. So you can check on your own if you want. Okay. All right. So that was horizontals. Now we're going to look at verticals. Okay. So I didn't end up changing my window. If you did, just go back to negative 360, positive 360, 90, and so on. You've got your y equals sine x already in there. Now, if we want to replace y with 2y, in your calculator, you have to get y by itself, right? So we would then have to divide both sides by 2. So we're just going to show that with the 1/2 out front, okay? Tends to be that we show it as a coefficient instead of sine of x over 2, but the same thing, okay? So now, if we graph this one, I'm going to keep that, clear off that, and again, do you have to use a fraction? No. Okay, 1 divided by 2 sine of x. Remember, in your graphing calculator, this goes 1 divided 2 times sine x, which is what we want. This is not 2 sine x in the denominator. You wanted that, which a lot of people do when they make mistakes. Okay? So just realize, unless you have to have brackets if you wanted it that way. There's your original. Okay, so now, same x-intercepts, but now it's not going as high or as low, right? It's squished vertically. Okay? Now the nice thing about vertical transformations, when you solve for y, it looks like it should be. It's a half in front. So it's half as high as it was to start. Okay? So it's a vertical stretch. So when y is replaced with 2y, it's still going to be the reciprocal here. But the nice thing is with these, is if you solve for y, then that's what the vertical stretch is. You can't do that with the x's, right? So, this is vertically stretched about the x-axis by a factor of 1/2. So now that 90, 1, so trace 90 in the blue there. Now if I cursor down and put 90 in, there it is there. It's half as high, 0.5, which is 1/2. So you can put 1/2 y, or you can put y over 2. Same thing. Okay, so here it says sketch the graphs of y equals sine x, and I have y equals sine x. So remember, we solve for y, we get the 2 in front. So I'm going to delete, okay, 2 sine of x. So based on the last one, you can probably guess that it's going to be a higher and a lower, right? Stretched out vertically. What points are invariant? X-intercepts, yeah. There's lots of them. There's an infinite number, right? As it is to infinity in both ways. We'll talk a lot about that. We're going to spend about a month on trig. A big part of 30-1. And we'll talk more about this trig graphs, right? We've already done all this fractal stuff. But the x-intercepts don't change. In this case, the y-intercept doesn't change either. That's only because it's through the origin. Okay, so this vertically stretched about the x-axis by a factor of 2. Okay? Because remember in here, this is going to be y equals 2. Okay, so 90, 1 will become 90, 2. Mapping x into 1. Okay, if we replace y with 3y, then remember if we solve for y, it tells you what happens, right? So if you wanted to do that, you can. And that tells you that now it's a vertical stretch about the x-axis by a factor of 1/3. And then if you replace with 1/3 y, it's going to be stretched by a factor of 3. So we're going to summarize in those parts. Okay, so if x is replaced with kx, the graph of y equals f of kx is the original. We just did it with sine, but this is for any graph, any function. So that's going to be horizontally stretched about the y-axis by a factor of 1 over k. Take the reciprocal. Whether it's a fraction to start, whether it's a whole number. Alright, just take the reciprocal. So the image point then, so if it's stretched by a factor of 1 over k, that's actually what you're doing. You're taking your original x value and multiplying by 1 over k. So, invariant points, what happens? So, maybe, well, I guess they don't have the graphs there, right? They're gone from their calculator. Where would the invariant point or points be? There's a bit of a hint in this. We're doing a horizontal stretch. Y-intercept, right? So the last one was vertical stretch, which were x-intercepts. Now we're going this way. Playing the accordion, the middle stays the same, right? So anything on the y-axis. Now, if we're dealing with a function, there's only one y, maximum of one y-intercept. Okay, so the invariant point is the y-intercept.
How do you write out a non-function in terms of like y and x? Like let's say
There would be x's and y's, squares, stuff like that. You don't use function notation. So you can still do the transformations in a similar fashion, but we wouldn't use function notation for it. Okay, then here for vertical, we're replacing y with ky. So here, this is going to be, so this is vertically stretched. Oh, sorry, too soon there. So this is going to be y equals 1 over k f of x. This is vertically stretched about the x-axis by a factor of 1 over k. So now your x stays the same, and 1 over k y. And now, notice how, because a hint here, there was no plural, this is plural, and these are the x-intercepts. Right? You could have negative x-intercepts, but sinusoidal an infinite number. Okay, polynomial are going to degree.
so it's whenever point is on the axis that you're reflecting the stretching.
Yeah, with the value there is 0. Okay, so I'm going to pick and choose here in the exercises. We'll do the first one. So y has been replaced with y over 2. Not a half y, but it means the same thing. So to produce the equation shown, the graph of the original is stretched. So if you're replacing y with y over 2, remember you're changing the y values. So that's stretched vertically. Now this says about the line. You're not going to say about the line x-axis. You're going to give the equation of the x-axis, which is y equals 0. And in this case, by a factor of, so here, reciprocal of a half is 2, or you can solve for y, to see that it's 2. So the image of that point will be x, 2y. Okay, next one has 2 stretches. Doesn't matter which goes first, vertical or horizontal. Because when you do them, you're dealing with a vertical stretch, you're changing the y value. Horizontal stretch, you're changing the x. So they have nothing to do with each other. So the order within stretches doesn't matter. So you can say it in either order. Notice how it's already been solved for y. So that for sure is the vertical stretch factor. So maybe I'll do that first. Is stretch vertically about the line again. So vertical is about the x-axis, which has the equation y equals 0. And that's by a factor of 4. Okay, because it's solved for y here. You could show this as 1/4 y. If you wanted to. It's also stretched horizontally about the line. The y-axis is x equals 0. Okay, by a factor of, so this value is 3/2, this b value. Okay, what's 1/b? That's the reciprocal, right? So you flip this, that's 2/3. Okay, think about this. This is bigger than 1. Okay, so when you flip it, it's going to be less than 1. It's going to be split. So you just take the reciprocal of the b value. Okay, so image then is x is going to be 2/3 x, and then 4y. Whatever that factor is, goes in the mapping notation. There are questions at the back, guys? Good? Okay. Take a look at question 2. Describe the transformations on the first function so that the second function is produced. Okay, so starting with y equals x cubed, just look for what's been replaced. So look for the brackets. X is now 4x. So if you replace x with 4x, okay, that's a horizontal because it's with x's. So horizontal, I'm just going to abbreviate with hs, okay, by about the y-axis by a factor of 1/4. Take the reciprocal. If there's brackets, it kind of makes it easier, right? Obviously, something's been substituted. Next one, there is no brackets, but look at what's the same. This is the same. This x is now this. Okay, so x has been replaced with x/2. So now, this is, again, a horizontal stretch about the y-axis by a factor of, well, x/2 is the same as 1/2 x. Take the reciprocal of a half. It's 2. again, no brackets, but this is the same, this whole thing, right? So now this has been replaced with 4/3 y. So that is going to be a vertical stretch about the x-axis by a factor of, this has been replaced, so it's a reciprocal, or you can solve for y. And then it would be the coefficient of f of x. Okay, this whole thing is the same. This is now 3. Okay, you can't get that by adding 2, right? You can't change the 1 over x plus 2, but to the result there by adding 2, you've got to multiply, right? Because it's a fraction. So, we're really taking this and multiplying it by 3, right? So, by going so this is the original. Now I've multiplied it by 3. Okay, so that's the same as replacing y with 1 over 3 y. This tells you that it's a vertical stretch. So now we're given mapping notation, and we have to describe what it is and state the equation. So this, remember mapping notation, it is what it is. So this is a horizontal stretch about the y-axis, or you can put that at the end. I always put it at the end, but keep it consistent. Okay, that is what it is. So the original function is y equals f of x. Now we're going to replace x with 1/2 x, or x over 2. Okay, the reciprocal. Okay, so next one, now x stays the same, y is now multiplied by 1/4. So that's a vertical stretch about the, oh, this should be the y-axis, shouldn't it? Horizontal stretch about the y-axis, vertical stretch about the x-axis. By a factor of 1/4. Okay, so if we start with y equals f of x, then you can go right to the final answer if it's solved for y. It doesn't say what form to put it in, so that, or this would be 4y equals f of x. See, I'm going to skip the wording on this. Let's just go right to the transform without showing any work. Okay? So you start with y equals f of x. This is a horizontal stretch by 1/3. This is a vertical stretch by 5. Okay, so that means this would be 1/5 y. This would be 3x. Okay, that's transformation form. Or y equals 5 f of 3x. I'm going to leave question 4 and question 5 for you to do. And then let's go to some graphs. Okay. Question?
Could you put brackets around or the like brackets like the 5 that I think the X all brackets to the 5 also? Why? You don't need
Okay, this means multiply. There's nothing there. Okay, so we're going to skip 4 and 5. Let's go to 6. So, what's graphed here? Y equals f of x, where f of x is the absolute value of x plus 1. That's your base graph. Okay? There it is. It's the thicker one. Folks listening, please. Okay? That's sketched along with 2 others, 1 and 2, with a new graph called G is equal to 3 times f of x. Then which graph is it? So think about, if we've got 3 times f of x, that's a vertical stretch by factor of 3. So here's your original. Your y value is 1. Always go to the y-intercepts. It's the easiest point. Happens to be the vertex, so also a good point to look at. Okay, y value is 1. If we multiply 1 by 3, we get 3. Kind of obvious what it is. Okay, so this is graph number 2. You don't even have to check the other one. Okay. Then it says, write the equation of g of x in terms of x. So, there's your original. If we're stretching by factor of 3 here, so g of x, we're just using function notation. That's going to be 3 times whatever f was. Get rid of those brackets. Okay? And then you could actually, check it on your calculator if you wanted, because it is in terms of x. Then h of x equals f of 1/4 x. So that's a horizontal. Okay? And so horizontal, remember, it's the y-intercept that doesn't change. And so that's why it's number 1. Not a huge number, like it's kind of obvious, but if you had more than 2 choices for these, you'd have to look at maybe a little bit closer. But here, if we're taking this point and we're horizontally stretching it by 4, we are looking at the x value there, 0. 0 times 4 is 0. So, say there was another graph to choose from. Let's choose another point. This point here has an x value of 2. Stretched by a factor of 4 would be 8. That would give us this point here. Okay? So you can check with more than one. Certainly if you're graphing it, you have to do it for more than one. So that's graph number 1. We're calling this h of x. And we don't even need to know what the graph looks like or anything. We have the definition of f. And by function notation, we're replacing x with 1/4 x. There's really no work to do, right, for that. replacing x with something. You're just replacing y. Whether you have function notation or the actual equation of
Even if
the
it's,
function.
like, let's say if f of x was like, f of x plus 2, it could still be 1/4 of x plus 2.
Yep. Let's say f of x was 4x to the 10 minus square root of x. You replace every x with 1/4 x.
It's not like your reflection when you can factor it out.
Yeah, like you could factor afterwards.
No, like you're saying with the, like, if you do reflections, if it was x plus 1, you can't change negative x plus 1 to negative x minus 1.
For vertical.
Yeah.
So horizontal, you just replace it.
Okay.
Yeah, so that's why the vertical there, it looks different, right? Okay, so, next one. Good old parabola, right? So state the domain and range. Hopefully, you know by now, the domain of any parabola is all real numbers. Okay? Range, look at the vertex. Okay? You can use interval notation now that you've learned that. I just use set over. I'm going to double page this. Okay, so description of transformation. Y has been replaced with 2y. So that's a vertical stretch. To save space, right? It's small in there. Just use ds. You can say about the x-axis, you can just do by factor by, in this case, 1/2. Just to save space when you're doing something. But remember, on a test, you're saving all the words. You've done it enough today that you realize that. Okay. Image point then. Okay. Domain doesn't change, so again, it's going to be fast. X element of the set of real. Okay. Now, we didn't have the graph, if we were just thinking about it, and we knew that the original was y greater than or equal to 4. We're stretching by 1/2. That 4 now becomes 2. So it's going to be y greater than or equal to 2. Okay. Invariant points, we need to know, we're doing a vertical stretch. Does it cross the x-axis? Right? Because those are the invariant points. Looking at that, there aren't any invariant points. It doesn't cross the x-axis. Okay, so we need that one. If we graph this, vertically stretching by 1/2, take some of the points. We plotted a few for you. So the vertex, 4 times 1/2 is 2. Y-intercept, 8 times 1/2 is 4. This is going to be the same over here. 1, 2, 3, 9, 4, 16, 20. Yeah, we actually do. So you can kind of, you'll have to estimate the other one. It's kind of being out here. Now with parabolas, there can be a vertical stretch that gives you the same result as a horizontal stretch. Okay, just be aware of that. Okay, so kind of done this to squash this, right? Replacing x with x over 2 will be a horizontal stretch. by 2. Okay? So this is going to be 2x y. Now, if your domain is all real numbers, and you're doing a horizontal stretch, what happens to the domain? Still all real numbers, because we're going to infinity. Stretching infinity is still infinity. You don't have a finite end to it. So this will stay the same, and your range will stay the same. Okay? What will be the invariant point? The y-intercept. Okay, so that's going to be 0, 2. So, horizontal stretch by 2, I'll do the vertex. So you take your x value, multiplied by 2 is 4. This point, we already said it's invariant, because 0 times anything is 0. This here, 4 times 2 is 8. And it's still going to be a parabola. It's still going to have that axis of symmetry. It's just a different one, right? So this is going to go up like this. Okay, and then the last one in the chart is got both. So this is vertical stretch by 3, horizontal stretch by 1/2. Okay, so then we'll have x and y. Again, if your domain is all real numbers, or your range is all real numbers, and you're stretching it, it's still going to be all real numbers. In this case, the domain is. Now our range, that vertex is now, that all the points are stretched vertically by factor of 3, so that y value 4 now becomes 12. So this is going to be y greater than or equal to 12. So 12. Oh, sorry. Do the x's as well. So here, sorry, I got to do both stretches. So x value of 2, stretched by 1/2 is 1. Y value 4, stretched by 3 is 12. Okay. Take another point, this. Stretched by 1/2 stays the same. Stretched vertically by 3 is 24. It's going to be way up 5. And then same thing here. So 4 times 1/2 is 2. The y value, so it's going to be really skinny. Okay. So there's no invariant point.
Yeah, it's the only invariant point to be origin.
Yeah. Okay. And that finishes it. Another way to check, just when you're looking at a graph, in your new graph, right? So here in your equation here, you want to put in your your x value on your original, multiplied by 2, gets you back. So, that's not starting very well. So here, in order to keep the same y value, we'll go back to this one. This has to be twice as big as it was before, right? So for every x value, it has to be twice as big if you're dividing it by 2. So that's why it's a horizontal stretch by 2. Okay? So you have to do that to get it back to the beginning for the x's. This would have to be half as much as it was. Okay? In order to get back to the original. Alright, so